Welcome everyone to the latest workshop. These are the pre-Clojure workshops on various topics in data science and machine learning. Today's presentation is an introduction to linear algebra with Neanderthal. Our presenter is David Pham. He's coming to us from Zurich, and he's an Emacs user, so near and dear to my heart, and an applied mathematician. So we are very fortunate to have him as our presenter, and we're really interested to see this topic. I think there's a ton of interest in it. So take it away, David.
Hi, everyone. My name is David Pham. So I'm an applied mathematician, and the goal of this presentation is really to give you an intuition about what linear algebra is. And to support me for this task, I wrote slides that I put in the Zulip chat. And during this presentation, I'll just go through the document and explain all the concepts, and with some graphics as well. So we're going to start with the slides. So, as I said, the goal here is really to make sure that anyone who does not know what linear algebra is will get out from the presentation with some kind of idea of what it is and could explain it to someone else. I need to precise here that linear algebra has two sides, and one is the theory part that I'm going to present today, all the concepts and why it works, and then the applied part, which is numerical linear algebra. And this is more what people usually are interested in, is like how you can solve problem with linear algebra. But the reason why I will not present this part is because if you want to understand the second part, you really need to understand the concepts of the first part of the theory. And if this presentation goes well, then maybe we can do a second session on the second part. So there will not be a lot of math, I hope. It will not be always precise, so please be kind to me. In terms of precisions, I'm talking about mathematician precision, so I hope it still be good enough for most people here. And what we're going to cover during this presentation are just what are actually linear vector space, or in which kind of constraints are we talking about when we speak about linear algebra. What are the functions that we use, or what are kind of mappings we use in the space, what a matrix is, what are eigenvalues, and then we're going to describe some special matrices that are quite useful in practice. And at the end, we're going to go through Neanderthal API. And as I said, numerical linear algebra is a topic by itself, and I hope we can cover this in the next session. Obviously, I'm quite used to have questions during my presentation, so if you have any, please just interrupt me. I really wish to clarify everything on the spot and not answer them at the end, because then we forget everything and we miss the context. So please just interrupt me, and we'll try to clarify things. So during this presentation, I'm going to try to start always from something that we kind of all understand, or we have some experiences, and then start to make some abstractions on top of it so that we understand where the concepts come from. And what linear algebra is in the end is to extend our understanding in geometry or of spaces, and try to extend this to higher dimensions. For example, what does it mean to have a space in 4D or 5 or 6D or 100D? And what does actually 100D means, right? And since we have this abstract space, we also want to generalize notions such as distances or transformations that do not change so much, such as a rotation. We have some kind of shape and we rotate, still the same thing, but what does it mean in higher dimensions? And in the end, we want to see if in these transformations, we can have some special structures to make this more efficient to apply. And so, as I said, as software engineers, we're kind of like more interested in practice. And if I had to describe this in like simple words, linear algebra is the science of adding and multiplying numbers. Yes? So linear algebra is the science of adding and multiplying numbers really fast and without any for loops, at least user-defined for loops. But what are we talking about really? So I think this is something that we all have once experienced. It's just we have two vectors. Vectors here is just in 3D, or just like a vector of 3 numbers. And we also have another vector of 3 numbers, and we want to add each element, right? So this is intuitive in a sense. If we have real numbers, the additions between 2 vectors is simply the element-wise addition. So this we all have encountered, and it seems like kind of like a natural extension of the plus operation. Here we can actually also remark that the complexity is O(n). Usually we also have what we call the scaling. Scaling property is usually we have a vector, and then we want to multiply each element by 100 or 1000. And so this kind of like makes sense to say, okay, if we have a vector and we have a coefficient, we want to make a scaling of each of the elements. And so this is the second operation that we're interested in, which is scaling. And this still has O(n) complexity. And then now I'm kind of spoiling the thing is, this is the heart of what we're going to try to do. It's called matrix multiplication. And I explain to you in the end what matrix multiplication are, but somehow we are interested in this operation in practice where we lay out our numbers, and then we can operate what we call a matrix product, which will result in a matrix where each elements are just a dot product between the vectors. So this element here is simply the dot product between this row and this column. You don't need to retain the formula here. It's really just to show you why it would be useful. And the complexity of this is O(n) m times p, which is like the number of row here times the number of row here times the number of columns here. And this is where we're actually going to get a lot of speeds in practice. So we try to really improve and be as efficient in doing these kind of operations. In the case where we only have one column here, that's an O(n) square. In this case, where n here is the number of columns. And if the matrices have the same size, then it's an O(n) cubic. So the whole idea of why we would use Neanderthal is to make sure that these two operations are as fast as possible. And here I just give a simple example, like we have vector v, which is just range between 0 and 3. Here w is just random integers. Here we have a random scalar number. And so the operations are just defined like this. In Clojure, you could say just like map plus vw, which is just 0 plus 3, 1 plus 2, 2 minus 1, and 3 plus 0, which is this result. And same thing for the scaling. Here, it's just a partial times multiplication of the scalar, and you would get the result. So 3 times 0, 0, 3 times 1, 3, 3 times 2, 6, 3 times 3, 9. And here I show an example how you could implement the matrix product. Yeah, it's not with a bit of exceptions, but more or less, this is actually the whole reasons why we are going to study linear algebra, is to make sure that we understand these kind of operations and we can perform them as fast as possible.
Quick question.
Yeah.
So you say we want to do linear algebra operations as fast as possible. Is there a particular reason why these things are performed at vast scales that would?
Yeah, that's I'm giving you the domain on which we're going to apply linear algebra in this section, in this slide. Okay. So first is, in terms of theory, we can ask ourselves, so how can we interpret vectors and matrices? What are the matrices? So in the matrix, what does a row or columns represent? And do we get more efficient representation of matrices? And that's going to be answered at the end. And the reason why we want to make this as fast as possible is linear algebra is used in all these domains here in statistics, machine learning, simulations, graph, and engineering, more or less, with optimizations, computer graphics, and solving partial differential equations. I can tell you more about the example. Is linear algebra gives us a good vocabulary and good notation for solving problems when we have a lot of dimensions in our stochastic systems. In machine learning, actually, linear algebra is abused, and it's kind of the king now with deep learning and natural language processing as well, which use deep learning, and also in reinforcement learning. And the reason why it's used is because it's used a model in statistics, which is a regression model plus some kind of other functions, and they compute this extremely fast, so they can pile these models on top of each other. And that's why it's one of the reasons why we have so much advances in what they call AI. So that's a good reason why to study linear algebra. Then we have what we call Markov chains, which you could say it's still something about probability or statistics. And it's more or less about systems that evolve and have some kind of randomness in the way they evolve. And yeah, finally, the graph and networks. This one is a good example. When you have small networks, you can compute the degrees of connectivity between each of the nodes and vertices, but it's not something where I'm extremely knowledgeable about this. And also in other traditional domain, linear algebra is used to solve partial differential equations, which means that we have these physics equations and we have constraints, and we try to understand how the physical systems behave and try to be able to predict how it works. And to do so, you don't have any analytical forms of the solutions. You need to perform simulations and solve these equations, and linear algebra is used there. So you could see it's quite useful, but personally, I use it mainly for statistics machine learning.
So question, why do you say it is abused for machine learning? I assume that's somewhat tongue-in-cheek, but what do you mean by that?
Well, the thing is, if you look at the advance of the last 5 to 6 years in machine learning, it has mainly been about deep learning techniques and deep learning architectures. Then if you look into these paper in this domain, then what you see is they mainly do matrix operations. So these ones, they do these multiplications, and they just make a lot of them during their estimations and their training. And that's why I say abuse is you don't have like, they state the size of their models by the number of operations of matrix multiplication they do. So that's the reason. Did I answer the question?
Yeah, I get it. So, rather than, major advances in technique, they just throw massive hardware at the problem. So that's
and even there, actually, I was talking about deep learning, but we have this operation called the convolution in computer visions, where you actually weight pixels, and the weight is done by multiplying a matrices and like taking these matrices and scanning the whole picture, and you reweight actually the pixels with each other using these matrices. And to get this really fast, you need linear algebra. Just a second.
Got it. Thanks.
Yeah. So yeah, now I just motivated you to study linear algebra. And now the question is, why would you need Neanderthal? And the reason is simply just speed, right? Because I wrote here some simple implementation of the vectors or the operations, and it works. I mean, for really small scale, I mean, like below hundreds of dimensions, that would be really slow, but it probably will work. But then the issue is you will just not be able to use all the engineering advances we had in the last 10, 20 years, which actually implemented these operations in hardware at the hardware level. And all the CPUs and GPUs, they all have these special instructions already implemented. And then what they call is single instruction and multiple data, where we say basically you have a plus operation, but on multiple data. And that's the reason why you would need to use a specialized library, because then you could leverage on these advances in terms of hardware. And the difference is not like 1 or 2 or 3, 4 times faster, is really like 1,000 times faster. And maybe you will see, you can see this when I show you the bench between Neanderthal and some kind of naive implementation. And to be fair, these advances allowed to create new algorithms. As I said, we spoke about deep learning, and that's only came thanks to GPU computing, because we were able to do these matrix calculation extremely fast. But in the field of statistics, thanks to the speed up, we could make a new field of statistics, which is just saying, instead of computing all the formulas by hand, why are we not trying to simulate from the model? And that field is named now the bootstrap methods in statistics. So speed is really important in this case. I didn't say it before, but I'm packing like a whole semester of linear algebra into these 90 minutes. So if I go really fast, just try to stop me, and we'll try to make it a bit slower. So the few concepts now that are important. Everyone can understand what the volume is, like 3 dimensions. Most people understand what 2 dimensions are. As I said, additions and the scaling in these spaces makes kind of sense. But the question is, can we actually think about what we really need from these 2 examples and try to generalize them to higher dimensions? And mathematicians came with like this cool definitions called vector space. And a vector space is simply a space. So you can think of a space as a set of elements or a set of things, which usually is infinite, where we have 2 operations, which is the plus and the scaling. And these operations are stable, meaning that if you perform these operations, then the result is still within the space. And the operations need to respect these rules, meaning it can commute, the addition should commute, it should be associative, meaning somehow you can perform the operations in any order and it will still be the same. Here is a mistake, sorry. You should have a neutral element, meaning that you should be able to add something to it and it will still be that something. You should need to have an inverse so that you can go back to the neutral element. Then you need to be able to also scale by 1. And this is sometimes not respected, but usually it is. And it should be distributive as well. So these rules, you kind of say, why do we have this? Because they're kind of natural, but they kind of impose a structure on the vectors, on the space that we're going to use. I have to make a pause for a few seconds. Give me a sec.
Much better.
Yeah, I'm sorry. I had the kids and everything. It's not so easy like this. Yeah.
No worries.
Yeah, home office plus quarantine and COVID does not make a good good mix. So yeah, so as I said, these operations, you could say they kind of seem to you natural, because it's the one that you use to actually multiply numbers. When you use the addition in your when you use addition in your code, usually you can assume you can commute it. But that's because we use real numbers. When you go into abstract space, you need to impose this. But as I said, in this presentation, we're going to mainly focus on the field of Rn, which is just simply a vector of real numbers. But the most trivial ones are the surface and the volume. And then we are gonna, in this presentation, we're also gonna think about what is a distance and angle, and to understand what these are in higher dimensions, we need to introduce what they call the inner product and the norm. So the inner product is simply a generalization of what you know about the Euclidean dot product, which is just the sum of the product of the components, which I defined here. These operations actually have some kind of mathematical properties. Is it that it's always positive? If it's zero, then the elements in it has to be zero. And it still respects this property of being linear, in a sense that you can distribute it and you can get out the scaling of it. You can switch the order of the scaling and the operation. And also you can switch the order of the elements. It's symmetric in the sense of the argument position. And in the machine learning literature, it's usually written like this. V perp W, which is the Euclidean product used. So every time you see this, think about this. And thanks to the inner product, you can now generalize the notion of length, a length of a vector, and we call it a norm. And with the norm, you can even define the distance. And maybe it's time that I can maybe show you how we can represent vectors in R2 so that you don't get totally confused. So let's say we have vectors here. Vectors is simply like you go from the origins and you take the value of them. So let's say you have the vector which has value -2 and 2, meaning that it's going to be an arrow that goes from 0, 0, 0, the origins, to the point -2, 2. So in this case, until here. And then you define a second vector called y, which is going to go from 0, 0 to 1, 1. So 0, 0 to 1, 1 here. So here you define two vectors on the plane. And now the addition of these two vectors, x plus y, is simply to take this vector xy and put it next at the end of y. And then we just do the path from here to here, which lands us here. And so x plus y is going to be, in this case, -1, 3, and we check -1, 3. And finally, the scaling here is simply just you go along the direction of x with a scaling of 0.5. What you do is simply you just go in the direction of x, and then you go half of it, which lands us here. So,
question.
Yeah.
Is there a geometric interpretation of the dot product?
Yes. Yeah. So usually, you can use the dot product to find what you call the angle between two vectors, because you can say it's the norm of it's a product of the norms times the angle between them. So that would be the geometric interpretation. And it's quite used in terms of similarity distance in machine learning as well. Does it answer your question?
Yes, I was wondering if there's a graphical example.
Yeah, so for example, no, I didn't do the graphical. But let's say you make let's say you make the dot product between y and x, right? So if they had the same length, let's say here I think with x prime, then the dot product would be equal to the cosinus of the angle from these two here. And then you could interpret this as the angle between the two vectors. But then once we go into multiple dimensions, we it's a generalization of these concepts. And what you would expect is if the two of them are aligned, then the cosinus between the two vectors will be near 1.
Got it. Thanks.
Oops, sorry. Okay. So yeah, these two concepts here, they generalize the notions of distance with the norm, and the inner product gives you a generalization of the angle between two vectors. But it's this interpretation I don't really like, because somehow you don't use it so often, and the angle in high dimensions is a bit, yeah, it's a bit difficult to justify, but it's my experience. So now what we just did is saying, okay, we're only going to get interested into space which has two operations, the plus and the scaling, and they respect some structure. These spaces are infinite, but they're quite big. And the question is, can we find substructures in the space in which you still respect these two operations? And that's what we call subspaces. For example, in the volume, you can have subspaces that are also vector spaces. That is, where all these operations, all these properties are still respected. And for example, in the volume, you could have subspaces, and these subspaces are the form is either a line inside the space or as a surface inside the space. And maybe I have like that, yeah, here. And here I have an example. So here, let's say this would be the space. This is like the volume. You have the whole space, and you want to define subspaces inside the volume. So as I said, it would be a surface or a line. And in this case, you could see that the orange area is strictly a subspace of the volume. But if you take any element inside the orange surface here and you add them or you scale them, then it will still be inside the surface. Same thing with the blue surface here. And plus you can see they're perpendicular, but that's something different. So here it's important to understand that we might work with spaces that are extremely big, like R100 or are with 200 dimensions of size 200, but maybe we're only interested in spaces that are actually only have a dimension of 3. And I'm going to speak about what dimension is right now. But what is important to understand here is to say there might be subsets of the space in which we're working that are still vector spaces. And since they are vector spaces, all the theory that I'm talking to you now will still be valid inside them. And we spoke about dimensions before, and I didn't define it. So now is the time to define it. And for this we need to speak about a bit of the notion of information in the list of vectors. So if you use a vector space, then you can take n elements inside these vectors, and we say that they are linearly independent if the only way to get 0 as the linear combination of each of the elements is that every coefficients in front of the vectors are actually 0. What it means is if you take a list of vectors, they all have some kind of information. You can think of it like this. And if one of them does not contain new information, it means that it could have been replaced by some linear combination of the previous vectors, of the other vectors. And so usually what you do in practice is you just take candidates of vectors, and then you check if they're linearly independent. And when you have one that is not, then you remove it, because you could just replace it with a linear combination of the others. And before I was speaking like saying, okay, you have this big space and you don't have the notion of generation. What you could do is just going backward. You can say you take some few vectors inside a space and you say, okay, every linear combination of these vectors will generate me a new space. And here you have to take my word for it, but it will be a vector space as well. Yeah. And now if you can find a list of n vectors which spans the whole space itself, that is, like if you take any element of this big space and you can express this element as a linear combination of the elements of the list, then we say that this list is a basis if the list is linearly independent. And if that list is finite, then the number of elements inside this list is the dimension of your space. This is how important. And as an example, if we go back to here, the space has actually a dimension of 3 because R cube, and the surface has a dimension of 2 because this can be generated by 2 vectors and not less, because if you have only 1 vector, then it's going to be a line. So the dimension of the surface is 2. Even if it lives inside R3, the dimensions is 2. Any questions maybe at this point? No? Okay. So yeah. So now if you have a basis, then there are actually certain type of bases that are a bit more powerful than the others. And the bases here, which is important, are those that are what we call orthonormal, meaning that their scalar product is equal to 0 if it's not between each other. That is, if you take the list of E1 to En, they're equal to 1 only if the 2 indices are equal. And the most famous one is probably, and the one that we use all often, is the canonical basis, which is just saying 1, 0, 0, 0, 1, 0, and 0, 0, 0, 1, which is kind of like the usual basis for what we do for representation. So I'd like to just summarize here. I think it's important is, here are all the concepts you kind of need to understand vector spaces. You take a set of elements, you put 2 operations on them, the plus and the multiplication. They respect some kind of properties, which are kind of intuitive for you if you're used to real numbers. You generalize the notion of angle and distance through through the inner product and the norm. And you define what a subspace is, which in this case is saying that it's a subset of the elements, which is still a vector space. You define what the dimensions are by saying, if you find a list of vectors that all contain some information and it spans the whole space, then this is a basis. And finally, some bases are more powerful than others because the elements inside the list are perpendicular. That is, like they have a scalar product of 0 if they're not equal to themselves. Right? So once we have these spaces, the question is like, what can we do with them? And most of the time we're going to do transformations. And the kind of transformations that we want to study are called linear mappings. And a linear map is simply a functions where you can kind of swap the parentheses with the plus and the scalar multiplication. This is mostly the definition here. If you take a combination of vectors, of plus vectors, and a scale version of it, then it will be equal to the scale version of the image plus the image of the second argument. So basically, you can just swap the calls between the scaling and the plus and the function call. Some example of this is simply saying in the plane, you say you have a vector v1, v2 in R2, and you just like take the opposites of the second argument. That would be one of the examples of functions that interest us. And there are a lot of them actually. So rotation, scaling is also a transformation, a linear mapping, and all sort of them. But then you could ask, a second example of this, which is not trivial, is simply the operator to differentiate functions is also a linear transformation. If you ever did some function calculus, then you'll see that this is how we define the derivative operator, and then you can see it's also equal. And so if you're interested, you could do linear algebra on the space of functions that can be derived. and you could still have this. Yeah, and what we also observe is the space. So this is going to be a bit more complicated, but the space of functions that are linears between two space is also a vector space, meaning that if you take a linear combination of functions and you define like this, then it's also a linear function. And this is going to be important because what we want to prove in this case is matrices are also linear mapping, and then we can apply all the theory on it. Then also something important is we can also observe that if we compose linear maps, then the resulting operator will be a linear map. In this case, maybe I'm going to read this is if you have an operator T that go from space U to space V, and you have an operator S that go from space V, so the same space here to a space W, then the product, which is simply just saying you chain them, is also going to be a linear map from U to V. And this is going to be important, meaning because it's how we're going to define the matrix multiplication, the dot product, the matrix product. So now we have all this. Why is it useful? So the space of linear maps that I just defined here in a more abstract way is bijective with the space of matrices. That is, for every matrices you can think of, then you're gonna have a linear map that represents it. And also it also means the space of matrices is also a vector space. But now the question is, what is a matrix? A matrix is simply just a rectangular array with numbers inside. And we say that the m times n matrix with m rows and n columns is a matrix of that form. And we usually have the first index being the rows and the second index being the columns. So these elements A1n means the element of the first row and the n column, and AMN is simply the mth row and the nth column. And the question now is how you go from matrices to linear map. So now we go back to the notion of basis. So let's say you have a map between, so map here is just a function for you to understand, which we could swap the order of operations. So if you take T that goes from V a vector space and W a vector space, V1 to Vn being a basis of V, so V has a dimension of n, and W1 to Wm to be a basis of W, then we could compute this, we can compute this transformation. We say, okay, we take one element of the first list, and we can express it as a linear combination of the elements of the second list. And the reason why we could do this is because this is a basis of W. So for every element, for every image in W, you can express the result as a linear combination of the basis by definition. And so here you can check the notation. Here we say, okay, for Vj, then we're going to say, okay, it's going to be equal to the linear combination of A1j times W1 plus AMJ times Wm. And so if you do this for the n vectors of V, then you get n also coefficients like this, and you can just like put them next to each other. And that would create what we call the matrices of the linear transformation T. I think it's really important. If there's any question here, I'd like to hear about it. No? Okay. So here it's noteworthy is it gives you an interpretation of the matrix in the end. It's saying, if you look at the columns of the matrix, then you know that this is just the image of the vectors of the first dimension expressed in the basis of the image space. And obviously the relation is bijective. So if you get the matrices, you can create a linear transformation between the first space to the second space by using this relation. And with this connection between linear transformation and matrices, then we can apply, actually, we can understand what the operation, the plus and the scaling operation is in the matrix space. Is simply if you have two matrices, then you want to add and scale them, then the ij element is simply the scaling of the ij element plus the bij element. And we can also associate this transformation to a matrix. Any questions now? No? Okay, so now we have this link between linear transformations. So just think of functions and matrices. And why are we have this matrix product then is because, as I said, the product of the chaining of function calls of linear maps is also a linear map. So let's try to make this example with like two transformation called SA and TB that goes from space U to space W. SA goes from space U to space V, and TB from space V to space W. Yeah, no, probably not this, but, and you define this like this. So if we try to compute the coefficient for uj for respect to s, then here is some notation, but more or less, here you express tuj in the V space with the coefficient of b because it was b here. Then since S is a linear transformation, you can swap sum and scaling. Here we just do the same step as before, where we express SVL as a linear combination as W's. So here we see that BLJ does not depend on I, so you can just swap the order of multiplication. And here we can arrange the terms. And here we see that the coefficients in front of the W gets into this operation, which is just simply you sum between one for the first vector, you do the dot product between the first row of A times the J column of B, because we were using UJ. And this actually proves and define what the product of two matrices is simply if you take the product of two matrices, then the coefficients would just be these expressions here. Yep. Any question? So these big demonstrations, so these few lines, just tells us like matrix multiplication in the end is just chaining linear maps between one after each other. This also tells us that you can probably not commute them, because if you apply one transformation and you apply another, it's probably not the same as applying the other before the first.
So okay. Is this all sort of defining composition?
In terms of matrices. So you have a one-to-one relationship between matrix multiplication and function composition.
And I take it this is useful because rather than having to apply a set of transformations one by one, you can create a compound
exactly
transformation by multiplying the matrices.
Exactly. So for example, one of the transformations I did not talk about is simply, for example, in this case here, we express T with respect to the basis of W and V. But then the question would be, is it possible to express this same transformation in different bases? And the reason why we would be interested to change basis is simply the matrix that we get at the end would be much simpler. And in this case, the chaining of operations means that some operations will be much faster. Does it answer your question?
Yes, yeah, it actually brings to mind somewhat of an analogy with transducers, where rather than serializing all the transducing steps, you can combine them into one operation essentially.
Exactly. So you could kind of confuse the transformation. But in practice, you would not do this because the matrix multiplication would be so much faster to operate. You probably would need to change you would need to reformulate your problem first, and then solve your problem in this new space and get back at the end. But that would be a subject for the next session if we have one about eigenvalues and transformations.
Okay, thanks.
Now we're going to have some examples of linear transformations because I think it makes much more sense. One of them in the plane is just a rotation by a coefficient of theta. If you want to rotate two elements in the space, and if you have this matrix, it will rotate your element. And here I found a really nice example of linear algebra for actually PDF. Because somehow if you want to scale or translate or rotate objects in the field, then you could use what they call like the extended basis for R2, which is saying you add the dimensions. Instead of having 2 dimensions in the plane, you add a third one. And then you have a matrix, so a linear map that will give you all these operations. For example, rotation about the origin, shearing, and also reflecting. So let's go with them one by one. If the matrix that you use has this form with x and y, if the first element was actually centered around the origin, the x and y will actually shift the origin vector to x and y. You can also scale around the origin by actually having these two numbers being changed. You can rotate about the origins. As I said, this is a previous matrix. So you could just like do this. You could rotate the elements. And the reflection is one of the most famous and the most used transformation. Is just saying you just put -1 in front of the signs. So if you want to make a reflection around the x-axis, you would do this. And if you want to reflect about the y-axis, you could do this. And here what's interesting is if you want to perform all these operations, you can either work out the numbers by yourself. For example, if you want to make a translation and also flip, then probably you could just like use this matrix, and you could just put the -1 here, which will flip then the operations. But what you could do is just multiply the metrics one after each other, and you would get the same results. So now if you want to perform all these operations, you just need to think about the operations, the order, and then you can just multiply the metrics one after each other. Yeah. So I talk generally about matrices, and like it's mainly just square of numbers. But you still have some special matrices, right? That could maybe help us performing better operations and faster. And these matrices are the diagonal matrix, which is just saying all the elements outside of the diagonals are 0. So here is an example. This is diagonal matrix because the element outside of the diagonal are 0. You could have the block or bent diagonal matrices. In this case, you could somehow see in the matrix that the elements in the diagonal are not 0, but then you can form blocks of matrix, and outside of these blocks, of these square matrices, all the elements are 0. And so you could visualize this like this. You also have the upper and lower triangular matrices. That is like all the elements outside of or below the diagonal are 0, or above the diagonal are 0. And then you have also symmetric matrices, which is just saying that if you transpose a matrix, then it's equal to itself. And the transpose is just defined as this operation, which is just saying like you do this intuitively. And each of these structures helps us to actually speed up the calculation of matrices. And the most trivial one is the diagonal matrices, because if you do power of the matrices, then it's equal to the power of the diagonals. So if you do linear algebra, you really try to get at the end a linear diagonal matrix so that you can really speed up all the transformations. And this comes back to actually the questions, why would you do these composition of transformation is usually what you try to do is you will just transform the first problem into a space where the matrix is diagonal, and you will perform the power there and go back at the end afterwards to the original basis to get the solution. And now, this is the last theoretical concept that we have to understand is eigenvalues and eigenvectors. And the intuition behind these two concepts is saying, we'd like to understand the linear map. And usually it's easy to understand when we can isolate the vectors or the axes on which the map is actually doing its transformation. And in math, or it's kind of like to understand if there exists a vector and a coefficient such that this equation is respected. This equation means that if I apply my transformation on that element, what I will get is either a shrinking or an expansion of the same direction. So you can somehow predict and understand what this transformation is doing. This is important because if you have multiple of them, then you kind of know that the transformation on the linear combination of these vectors will stay within the same space than these vectors. It's what we call invariant transformations. And usually you try to get them when you try to solve when you try to solve long computations, because then it would give you a better basis and you can speed up computation afterwards. But it's basically a summary of your transformation. And
so,
yeah.
Some questions. I assume it's beyond the scope of today's talk, but there must be standard techniques for doing for transforming matrices to upper or lower form, or
yes.
and to find the eigenvalues.
Yes. So basically what you do here is solving a system of linear equations, right? And which is also one of the usefulness of linear algebra. We solve linear equations, and it's beyond the subject, but you would write this in matrix format and you can solve it. It will not be fast, but then you have some other techniques that would make it much faster. But Neanderthal has this function call to get the eigenvalues and the eigenvectors.
So you don't have to do this by hand. There are libraries that
there are libraries that's well defined. They have multiple. So basically, what you need is a solver first. So, and since most libraries come with a solver, they also wrap this solver around this equation, this specific equation, so that you also get the eigenvalues and the eigenvectors. I think I have an example afterwards in the practice session. And
presumably they're not always, those solutions don't always exist, and
nope.
So you get a failure or an error or something out of it.
Most of the libraries, I think they will go into complex space, and in complex space, then these solutions always exist. So, or not always, but I think there are a lot of chains that exist, depending on the conditions, depending on your problem, but otherwise it would fail.
Great, thanks.
Yeah, I have to study the theory. The existence and of the eigenvalues usually. So the real question here is, when can we? Are there sufficient conditions, or how as a practitioner we can make sure that we get these eigenvalues? And in this case, what we could do is we can use a preconditioning matrix or some transformations of your problem such that you know that eigenvalues and eigenvectors would exist, because we know some properties on the matrix such that we know that this transformation will have eigenvalues and eigenvectors. It's the whole conditioning of a matrix that we can think of next time for the next presentation. So I just finished the whole theory. Maybe I just quickly summarize for everyone is what's really important is linear algebra is concerned only with spaces that have these two operations, the plus and the scaling. We define what the dimension is, basically by saying we take a list of vectors inside the space and we make sure that each of them have some information, and we make sure that every element in the space can be expressed as a linear combination of the element of the basis. And the number of elements in the basis gives us the dimensions of the space. For all practical purposes, the canonical basis is the one that you will use. That is the list of vectors which have all zeros except one index which has one. And it's from this, from here. Here, you can extend this example to n dimensions. This is probably the base that you will use most often. Then the second concept that is really important is the linear mapping. Linear mapping is just functions where you can swap more or less plus and the times in the arguments defined here. And then we know that we have a relationship, a one-to-one relationship between the space of transformations, so these linear transformations, and the space of matrices. We also find out that if you chain linear transformations, then the chain function is still a linear map. So if we apply this to the matrices space, we can define a new operation called the matrix multiplication, where the index in the end, or the elements of the matrix of these products are given by this formula. And you can derive this value just by using the properties of that are written above. And then here we saw some example of transformations that are linear. We know that we have some transformations that are quite specific because somehow the way their coefficients make sure that they're really good for doing some computation. And if we want to understand the linear transformations, we can check their eigenvectors and their eigenvalues because they give us some kind of directions on how the transformation works. And now these are all the concepts. If you start to, yeah.
Sorry to interrupt. Can you just give us a reason for the word linear?
Yes, sure.
We all know that linear relates to performance, big O of n, for example, but
yeah, sure. The linear comes here. So it's basically it's inside this definition here, right? When you have the plus and the minus, the plus and the scaling, right? It only comes with the fact that you cannot have squares or you cannot have log transformation, cosinus transformations inside these functions. And
I see. So only basic multiplication
and additions, yes, exactly. Okay, and the multiplication is only about scalar, right? It's right. Not scaling each of the elements, right? In this case, for the scaling of each element, you would need a transformation for this. But linear also comes from this. I believe it comes from this equation here, where you basically can swap the function call with the homotopy, which just means that from the scaling, and you can also remove the plus and put it on the space of the function call, because you have an element in the input space, right? You apply t in the element of the input space, and what you force is actually you have the same kind of operations on the output space.
Yeah, it's the same shape. It's the shape exactly. of a slope.
Exactly.
Okay. So thank you.
And the reason why it's linear is because you respect this operation in the end. This is really concise way to express what linearity means in mathematics. And you have the same property in algebra, in matrices as well, right? When you can just, when you add stuff, and outside of the matrix product, you see that you still have these operations like kind of plus and multiplication, but multiplication is only on a scalar, right? Not multiplication between each other.
Thank you very much.
Yeah. So now we come to the practical part. I'm going to state a few notions that you need to understand to use Neanderthal. And yeah, afterwards we're gonna dive into some practicals. So Neanderthal follows quite well the LAPACK naming convention, meaning that to understand how you construct in the API, you need to understand the type of the content of your object, which is either a double, a float, or an integer. What kind of matrix structure you have, either is a vector or a general or dense matrices, a symmetric matrices, or triangular matrices. Neanderthal has many other types, but for our purpose here, we're gonna use the vector and the general dense matrices. And then the third concept is the runtime, which is either we use native, which leverage Intel MKL, CUDA, which use the GPU for NVIDIA's, or OpenCL, which is a multi-core, or ATI, or even NVIDIA GPUs. Depending on which combination of these three, you will have a different function call to create vectors or matrices. And for most of the problems, we're going to use the native vector and the native general matrices. I'm going to show you how to use them afterwards in the second notebook. And then all the functions in matrices is all the basic operations, which is like altering the elements inside your matrices, or the plus, minus, or scaling of the matrices are exposed in the core. If you want to use some specialized math functions like log, exponential, or square roots of each element inside your vector, the functions lived inside vectmath. And there's tons of algorithms from linear algebra that I did not expose that are inside the linalg namespace. Among them, you have finding eigenvalues, solving least squares, solving equations, and also matrix decomposition. If we do another presentation, then it will be, the topic would be to dive into each of these functions and know how they work. And for each of the functions, you usually have two versions. One is just a pure function one, where we don't touch the input arguments, and one that destroys the element and mutates them, and they all finishes with a bang. And then we can dive into some examples. Yeah. So here is a notebook using Clerk. And here you see that I'm going to use the native versions, which I aliases as UNN. Maybe you can have different notation, but I find it easier for me. And here, as you see, that I'm going to use the vector and the general matrices. In math, I usually use cos and sin. Linalg is going to be namespace as UNL. In the core namespace, you have AX plus Y, which is just saying you're going to make scale A, scale X with A and add it to Y. The MM operation, which is the matrix multiplication. Scale, which is scaling a single vector, and MV, which is multiplying a matrix with a vector. And finally, I have the random namespace just to make sure I can have some cool example easily. So here are some helper functions. And this is how you can create a vector. Simply call dv and then just have a list of vectors without any problem. Or the version that I prefer to use is the first argument is a vector, Clojure vector, and then you can initiate them like this. And then they're going to appear like this. And there's a third version of the constructor where you define the number of the dimension of the function call. Right? Here I gave you an example how you could create a random vector. And this vector would have a norm of 1. So here you create a random vector of size n. You use the destroying version of rand uniform. So it's going to be a vector of size n with random numbers between 0 and 1. And then you make sure that the norm of this vector is 1. this is what this operation does. Same operation for random matrices. And here is the API how to create a matrix of 3 rows and 2 columns. And you pass the arguments by columns. So here I have an example. So this call will first fill the columns, and then it first fill each columns one after each other. And here is how you could slice them with the call function. You use the call function, use the matrix, and then you have the index of the column. Here is a way to get a collection of the columns, and same thing with the rows. If there is any question, I mean, here I guess the added value is just we can go through the possible way of calling it Neanderthal. But the API, the documentation is actually much better for this. So if it's useless, you can tell me and we can skip. Here would be how you could create a rotation matrix, which would be useful for later for some example. Here, how you create a scaling matrices, like the example. And yeah, the operations, as I said before, here you just want to have x plus x. If you want to express this, you use the x plus y function, which is non-destructive. You also have a second version how you can call this function is with scalars, because here you could just put different scalars. And here is to compute the opposite of the vector.
Sorry, what is homothety?
Yeah, so it's just scaling.
Oh, okay. Fancy word.
Yeah, fancy word for saying it's a proper word for saying scalar, to scale.
Thanks.
Sorry. As previous, so here is an example how you could use the functions to make this example about plus and minus. These, as I said before, it gives you kind of a geometric intuition about how you can see the addition of vectors and the scaling of vectors. One of the operations that I appreciate people understand is like the scaling of vectors is simply like going along the line and make it bigger or shorter. Here is simply just the subspaces, how you can compute the elements of the subspace. And here is the function how you can make a transpose. Here is how you could make a matrix multiplications. So how you could use matrix multiplications to actually compute the points on the surface. And here is simply just an example how you could see like the linear transformations of a rotation, which it says we create the matrix of rotation and we multiply the original vector, which is this one, and we rotate it by math of pi over 2, which is 90 degrees on the left. Same examples, and here is a bigger rotation of 180 degrees, and this is like a 60 degrees rotation. And here we have an example of why matrices cannot commute. Basically, just have a simple example of how they don't commute. Any questions?
Just a comment. Back in computer graphics class, we were taught how to do these kinds of transformations, scaling, rotation, translation, and so on. But it was the foundations were never given the theory, so we just applied them blindly. And
I mean, what I like when in the example I showed before in the slides is, in the end, you can just compose the transformations. You have these simple blocks, and you can just multiply them next after each other. And I think it follows the Clojure philosophy, where you think about blocks, and then you can make a chain of function calls. And I really like this view on computer vision as well.
Yeah, and
And-
it's very easy to see the non-commutivity, I guess,
Mhm.
by doing a rotate and a scale in different orders.
Yeah, and also just like just if you translate an object and you make a rotation, it's not the same thing as making the rotation and translating and scaling as well, right? Because it's a scale around the origin.
Exactly.
Actually, yeah, it makes sense. Yeah, finally, I wanted to show an example of eigenvalues. You just take these simple transformations, which, as I said before, is the one that takes the opposite of the second argument. And here you can have the visual representation. You see, let's take the vector of 1, 1. And if you apply the transformation to this vector 1, 1, then you would get this orange vector. But then if you want to compute the eigenvectors and eigenvalues, you could see that they are actually the vector 1, 0 and 0, 1. So these red and purple vectors are actually the eigenvalues. And you could see that if I apply the transformation on these vectors, then they stay on the same linear space. So they stay aligned. And here you can see with the purple with 0, 2, 0, 1, if you apply the transformation, then it will still stay on the same line. And here you can have an example of how you could call the eigenvalues methods here, which destroys actually the content. And you would get the vectors themselves here. Yeah, and I think now it's time to conclude. What I hope really that you can take from this presentation is that's not sorcery, right? Linear algebra is just the study of linear relationship, which is just adding and scaling elements in finite dimensions. Adding and subtracting matrices and vectors are ON operations. So here the added value of a specialized libraries might not be totally visible. But then multiplying a vector with a matrix is ON square, and multiplying matrices like composition is ON cube. And this is where you might want to have a really good specialized linear algebra library. The vector space is just a generalization of what you would think of 2 dimensions and 3 dimensions, where we only consider addition and scaling. Vector space are spanned by a basis, so you can construct a vector space by defining the basis first, and the basis is just a list of linearly independent vectors. There's a linear maps basically are transformations that respect still they preserve the addition and the homotopy between the two spaces, and then you can somehow describe a linear map by the image of the vectors of the input space into the linear combination of the output space, which all brings us to the final results, which is saying matrices are just a representation of linear maps. And there's a one-to-one relationship. And for a given map, you can actually have different type of representation. There are some matrices that are better for computations, as I said, diagonal, symmetric, or band diagonal or triangular. And eigenvectors are just vectors which allows us to understand a linear map better. And there's a final point here is just saying, if you use Neanderthal, then make sure to keep vectors in Neanderthal formats, because if you start to switch between Neanderthal data object into Clojure vectors, this is where you're going to start to lose a lot of speed. And with this, I'm finished with my presentation. Any questions?
Yes, thank you so much. Great presentation. Enjoyed it. I have a question regarding the GPU, use of the GPU in the namespaces you mentioned.
These two?
Here, construction of matrices, vectors, functions on matrix. Could you just give us which one need to be used in order to do parallel computation? Would it be Neanderthal native?
So
CUDA and OpenCL? Does
sure.
Neanderthal native do parallelism? I mean,
Yes.
on the
No, so native will use your CPU, but it will still leverage the vector instructions inside your CPU. So it will already be parallelized. And to just
only parallelized to the extent that the CPU allows.
Yes. That being said, if you really look for speed, if you implement in native, you really need something around more than 10,000 elements inside your matrices before you might get some performance value from your GPU. Because my last comment was about transferring data between your native and Clojure format. You also have this penalty between GPU and native. So if you, my advice here is if you have an algorithm, start with the CPU and then try to separate the CPU and the computations out of it. And Neanderthal does it really well here. You would use the core functions, and the core functions works on both on all the objects, either GPU or CPU. So you could start with native, and then once you really need GPU, then you could just swap the constructor, and that would probably work.
Okay, thank you. So in order to use the GPU, you definitely have to call either CUDA or OpenCL.
Here you would have the constructor inside the CUDA, and then you probably have DG inside the namespace.
Okay, and I just had a follow-up question regarding the last point regarding the transferring between native and memory and Clojure. There is a TechML dataset project that I think mentioned that he has a copy operation that does that. Big O of one. Is that would that apply to this? Would you be able to use that here?
So that's the trick. Is if you need to start to use I/O, my advice is to use TechML dataset to import your data and then transfer it to Neanderthal. That would make things much easier for you because you could do the transformation in TechML dataset, and then afterwards you have the you could transform it to Neanderthal and use it there. My point was more, I have a third namespace, I think, a fifth namespace, yes, here. I had this question myself, is I mainly do web development during the day, so I can only use really Neanderthal. And the question was, at which point do I start to gain anything to use Neanderthal when it's not about really number crunching, right? So number crunching, you have some definite spaces where it makes sense for when you have to deal with images. So here you have already you have already thousands of numbers. So it already makes clear that you could get a speed up. But what if you only have maybe 300 numbers and you need just to make a plus between 300 numbers, or just 300 numbers and 300 plus, and then you have a scaling that you need to do as well. And I did this benchmark that is also in the slides that I provided. It's just saying, okay, I'm trying some scenarios here, and I'm doing the round trip to make sure to understand at which point does it make sense to start using Neanderthal. And that's also when I had a great discussion with Dragan, the creator of the library. He told me that you need to express the problems such that you can leverage matrix multiplication. But then I talked to this about later. So in this notebook here, what I'm trying to do is I'm trying here to see, okay, here is the dot product, and I'm just computing this benchmark of different matrix sizes or vector sizes. So here for a vector of 5, if you do the naive implementation with just Clojure, then it gives you 700 nanoseconds, and it would take you 2 microseconds with Neanderthal. And the reason why it takes so much time is because you need to transform your vector into a native vector and then use the function. And I did this experiment for multiple ends, And what you observe is already at 20, you already are break-even here, when you see, or 25. And starting 25, Neanderthal start to be faster than just the simple Clojure solution. And we can go on like this. So the dot product is kind of easy because you only have one direction of transferring data, because the result is a double. So you don't lose any time. But let's say you have a more complicated example where here what you do is just want to scale a vector. And in this case, you always lose. You can never, you do a round trip once to native, you do the operations, and then you need to come back into Clojure. And there, at any dimensions, transferring data just takes too much time. So you're always better off using raw Clojure here. You can see it. I tried with like 10,000 elements, and it's still twice faster, almost twice faster using just Clojure. But then here is a cool example, is like when you have to add 3 vectors, and there you see that it starts to get extremely fast already at 20 elements. At 20 elements, you start to, when each of the vectors have 20 elements, you almost break even with Clojure, but then afterwards you always win. And for example, if your vectors have a size of 500, then you're almost twice as fast. Yeah, and to prove my point, that you're losing actually a lot of time in the I/O, here's an example with the same numbers, but then I don't perform the I/O, just perform the plus operations. And here you see you already have, just for 5 elements, here you already have 1 magnitude of order. You're already 10 times faster, and it just goes much, it keeps increasing the higher you go with the number of elements in your vectors. In this case, you already have 500 times faster. Yep. So does it answer your question?
Yes, thank you very much.
So
I have another one for later, but I want to let somebody else ask questions. Thanks.
I have a bunch. So one is, did you benchmark the CPU versus GPU within Neanderthal? You mentioned something like the need of 10,000 operations to break even.
No, I did not benchmark this one because it depends on your GPU as well.
Right. Did you install the CUDA libraries? And
yes.
If so, was it is it difficult?
No. I use Ubuntu, so just install the CUDA. That is just check which version of CUDA you need with Neanderthal, and you can download it, and it's trivial at this point.
And that depends on your GPU card.
So NVIDIA cards, if you have a recent one, let's say less than 10 years, or let's say then like say 8 years, you could probably find a CUDA version which would match Neanderthal. Because Neanderthal updates its version for every CUDA version, so sometimes it's a bit, sometimes it breaks you when you update Neanderthal. But yeah. And
do you pretty much need a NVIDIA card, or can you can even get value out of, say, the GPU in a Mac or something? I don't know. So I don't think Dragan's plan to support the M1 chip. Right. Reason is because he doesn't have one, probably. Soon. We hope. That maybe we should provide him a Mac Mini so that he can hack it. That being said, the M1 chip was required to rewrite the backend, because he basically targets different backends, and CUDA is a backend, and you have a you also have a back API SDK for the GPU given by Apple, and there I could see someone writing the bindings for that backend if someone is motivated and able. I would be motivated, but I'm not really a good coder, so. Got it. And then also, that being said, CUDA has so much investment inside it that it's probably the faster that you can get, right? So, but as I said, it depends on the size of your problem.
and depending on the size, staying a native could be much faster. Yeah.
So some people might be best off getting a cloud resource or something, I suppose, rather than if you have a few one-time major jobs.
Yeah.
Although I think cloud GPUs are pretty expensive.
It depends. For this, I have some experiences. What you could do is just having spot instances in Google Cloud and in Azure, if you can get that. But otherwise, in AWS, it's quite cheap. It's like 20 cents per hour.
Oh.
So it's very good. I did not try to hack Google Colab in the sense that on Google Colab, you get a Linux machine with almost all admin rights, not everything, but enough to install dependencies. So probably there you could also have a cheap machines for free or for $10 a month. So yeah.
Cool.
Honestly,
Great.
if you want to try Neanderthal, I would really advise start with the native version, and then once you feel comfortable, then you can try to use the GPU, because the GPU adds some complexity out of it. We have to be honest.
Makes a lot of sense. All right. Any other questions out there or comments?
Yeah, I would be interested to know what kind of complexities comes with the use of the GPU in Neanderthal.
Um,
Do you have some sample so that we can take a look at what it looks like?
Yeah, so you can go on dragon.rocks. He has, let me check if I can find, he has a lot of articles on actually GPUs, and it's not a lot, right? Because what you need to do is manage the GPU memory, but in a sense that you don't want your objects to leak. So usually it's just having a with statement with the let me guess, with the statement with your implementation. Yes, yeah. Let me check if this is CUDA. And then context GPU manage GPU. Here I could give you an example. Sorry, it's in the chat. So here would be for deep learning, but let's check if I... Yes, this one, I have one for you. So the second one is quite good because it gives you an example. It's of GPU. Do you get it, Vincent?
Yes. You
So,
put it on Zulip?
oh yeah, sorry. Let me share screen. So here, this is one of the examples of Dragan. He actually is trolling a bit NumPy and QPy, and showing that actually his library is so much better. So basically, if you want to try to use, check here. So here is an example how the added complexity for having a GPU. It's basically these with release statements to make sure that they release the memory inside the operations. Yeah, I cannot give you much more examples, but somehow, yeah, this one here would be an example how you would use the GPU API. Honestly, the jump is not high, but it's really, you just need to make sure that you manage a bit of the memory specifically, like this here, where you need to make sure that you have some release and to make sure that it does not explode. Make sense?
Yes, thank you.
Could you give us, in theory, the maximum, because obviously GPUs are used to leverage the fact that many dot products can be done in parallel during matrix multiplication. What is the theoretical maximum speed up? Is it close to big O of n or n squared? Or is that, does that vary depending on the operation, on the matrices?
It depends on the operations. Well, no, not really operations. My experience is in machine learning. And for convolution, for example, where you really rely a lot on the convolution operations, so matrix multiplication there the difference is like tenfold easily. So using a GPU instead of CPU, you get 10 times faster at least. And that's the that's like the lower bound, I guess, because you have 3,000 cores against 8, so that's kind of like the so 3,000 is like a small number of cores. You can actually get like 5,000 easily. So yeah.
But in theory, the to say
no, I think
we cannot really put a number. It's still big O of n.
it will still be ON cube, right?
Okay.
It's just going to be the coefficient in front of the ON cube will be, well, technically it's not ON cube, it's like n 2.7 something, but you would still have just the it will still be ON cube, but the constants in front of the n cube here would be much smaller.
Okay. Thank you.
My pleasure.
All right, everyone. We are over time, so we need to wrap up. I would like to just give a shout out to some of the contributors in the Clojure community that made this talk possible. Dragan Jurek, of course, creator of Neanderthal and author of several books, including Numerical Linear Algebra for Programmers. Really great books, so check them out. Clerk was used for displaying the graphics and notebook style. That's Martin Cavalar. So thanks to him, we've gotten great use out of that in these workshops. And the criterion benchmarking, Hugo Duncan, really useful to do that kind of profiling and see the performance gains. So that's all I have. Do you want to say any last words, David, to your audience?
I hope they get something out of the presentation, and just make sure you can use your new powers respectfully and make good things.
Very good. And maybe you can offer any resources for follow-up for people who want to continue in this journey.
Sure.
Let's do that in the Zulip chat, and we can continue the conversation there. And so see you all there, and I hope you also will check out some of the other workshops and Reclojure and the post-Reclojure session that we have planned. So see you all there.
Bye.
Okay, bye all.